Nice to
Good
see you.
morning and good evening to you.
Yes, it's 7 in the evening, must be 8:30 in the morning for you.
Right, that's right.
Yes. Okay.
Yeah,
So
you people have time. You people have timed it well for me.
so nice. So nice to
Yeah.
see you. So let me take only 2 minutes to introduce you because I can't do justice to that. But everybody knows you, and so. But still, for completeness, Prashanta has given me this job. So you are a PhD from University of Rochester in 1969, if I remember correctly, and it was a PhD that was much talked about even after when I landed in Rochester and I graduated in '87. So Professor Agarwal is currently at the Texas A&M University. Many departments in departments of biological and agricultural engineering, physics and astronomy, and also at the Institute for Quantum Science and Engineering. His awards, very distinguished awards, the list of it is really long, so I won't really take so much of time, but I must say, starting from the Santi Swarup Bhatnagar Award given by the government of India way back, I think 1982 or so, I have seen him taking the Max Born Award of the Optical Society of America when I was briefly with him in Hyderabad, 1988, I think. Then, of course, he got the Einstein Medal for Optical and Quantum Electronics Society. He got the World Academy of Sciences Prize in Physics the same year, I think. And what made us all extremely proud once again was when he was declared the Fellow of the Royal Society. This happened, I think, in 2008. Is an extraordinary researcher, a recognized leader in the field of quantum optics, and had made really major contributions to the fields of nonlinear optics, nanophotonics, plasmonics. We'll hear from him today, but for me, it's really an honor and a privilege to have known him kind of closely for some time and to follow his work. He's one of those rare geniuses in theory who can look at an experimental result and know which techniques and which model to apply. And he has really solved so many problems by, with an efficiency that, I can only dream of achieving someday, but now. So today he would be talking about a special result. It's on time-reversed quantum metrology using squeezed states of light and matter. The connection with the previous talk, I mean, he would also be touching on open systems, not just unitary closed systems. So we'll be looking forward to hearing from him directly. So Professor Agarwal, 1 hour is allocated for this session. So towards the end, if there is time for discussion, that would be nice. If you could take maybe 50 minutes or so, it would be nice, but I leave the floor to you and over to you, and thanks.
Okay. Thanks, Rupa, for this nice introduction. So let me start by saying that I used to visit ISER quite often and have quite fond memories of visit to ISER starting from very, very early days. I'm also happy to see that Prashant and company have been organizing these QIQT schools for a couple of years now. And I think they are making a great contribution in preparing the workforce in the field of quantum technology for the future, especially now that the government of India has announced a new quantum initiative which would be worth 6,000 crores, So it's quite a good development that's happening in India. So today I'm going to talk about quantum metrological applications, especially the use of the squeezed light as well as the squeezed states of matter. So let me start sharing the screen. Rupa, can you give me the screen?
I think you have it. There is a green arrow at the bottom or the top share screen.
Yeah, I do that, but it says host disabled participant screen share.
The organizer, Prashant, can you see?
Let me ask our team, this QIQT people.
Sir, you can share now.
Yeah, you can. Yes, we can see.
You can see now? Okay.
Yeah, and full screen.
Yeah, I'm going to put it on slideshow.
Yes. Perfect.
Okay, can you see the full screen?
Yes, yeah, we can. Thank you.
Okay. So here is the brief outline of my talk. I'm going to tell you the basic elements of quantum metrology, ideas about the quantum Fisher information. So, and then we'll apply these ideas to both unitary as well as the open systems. Tell you what exactly I mean by the time reversed quantum metrology. Tell you a little bit about the squeezed states of light and matter. And then describe to you the quantum metrological applications using the photonic and the atomic interferometers, and show you how some of these situations can saturate the Cramer Rao bound, give you some experimental results on the quantum metrology of atomic displacements, and finally describe to you results for open systems, especially when you want to look at the loss and the scattering parameter. In particular, I'll bring out how the time reverse metrology setup can almost saturate the Cramer Rao bound. Okay, so this slide explains to you the parameter estimation in classical and the quantum physics. So let's consider a system which you want to probe using an initial quantum state. The, the quantum state undergoes dynamical process, and we get the final quantum state, perform the measurement on the quantum state, and then from the measurement get an estimator for the parameters. So basically you are looking at this quantity delta x, which would tell you how best you can do your measurement on a given parameter. And the natural question that we ask in connection with quantum metrology, that what is the best initial quantum state that you can use to probe the system? And second question, which is equally important, what is the best measurement procedure? And so both in connection with both of these questions, the quantum optical developments are quite significant. Okay, so this slide gives you the Cramer Rao bound for the unbiased estimation. So X is the parameter that you are estimating, and this is the kind of uncertainty in the parameter X, or how well you can estimate the parameter X. And so this is the Cramer Rao bound, which is in terms of the number of measurements and the Fisher information. So the Fisher information is given by this result. So here Pjx is the probability of getting an experimental result J. If you have continuous measurements, then you replace this discrete sum by this integral. Note that this expression for the classical Fisher information, it involves logarithmic derivative of the probability distribution. And this logarithmic derivative would be an aid to convert this expression into quantum Fisher information. Okay, so if we have a system, a quantum system described by the density matrix rho, which is a function of the parameters x that you want to estimate, then the quantum Fisher information is defined in terms of the expectation value of L square. L is the logarithmic derivative, and now this logarithmic derivative is defined in terms of the derivative of the density matrix with respect to the parameter via this relation. So as indicated, that this expression for the Fisher information in classical statistics involves this logarithmic derivative. When you are dealing with quantum systems, we have similar result involving this logarithmic derivative, but now the logarithmic derivative is to be calculated by using this. Now in general, it's quite difficult to calculate this logarithmic derivative. If you have systems which are undergoing unitary evolution, then I would show on the next slide, simpler expressions can be obtained, but for open systems, it's quite a challenge to calculate L of x. So now let's first look at the systems undergoing unitary evolution. And so unitary evolution for pure states, then one can show that this expression for the quantum Fisher information goes over into this expectation value, which involves this operator G, which is to be obtained from this result, where U gives you the unitary evolution of the system, and U is a function of the parameter that you want to estimate. So in many applications, you want to estimate the phase, and in that case, U would be related to the phase. In particular, if U can be written in this form, X is the parameter that you want to estimate, and theta is an operator which is independent of X, then this expression for the quantum Fisher information can be used to write down the Cramer Rao bound for the parameter X, which would be this. And this quantity is the uncertainty in the operator theta, and this uncertainty is to be evaluated using the initial probe that you are using to probe the quantum system. So if x is the displacement that you are trying to estimate, then corresponding theta will be momentum. This should be clear from this form. And therefore, this relation translates into this, which looks like uncertainty relation in quantum mechanics, but actually it's not. Delta P is the uncertainty in the variable P. However, delta X is the estimate of the parameter X. So that tells you how best you can estimate the parameter X. And so from this relation, you obviously see if you want to minimize this parameter delta X, then you need to have larger value of delta P. And so immediately the squeezed states would come to your mind because if you have squeezed states which are anti-squeezed so that delta P is large, then you would have a very good estimate of the parameter X. Now, one of the problems with the quantum physical information is that it tells you that what is the best this is possible, but it does not tell you what kind of experiment you must design to get this best value. And we will see later what do we do when it comes to experiments. Okay, so the idea of the time reverse metrology is the following, that we start with some initial state. So this initial state is used to probe the system. We apply an operation S, and this operation S prepares, convert this initial state into a quantum state. So by quantum state, this could be, for example, a squeezing operation. This could be vacuum squeezing operation. So you get the squeezed state here. And this is now used to probe the system. And so in general, this input state would get converted into this mixed state. If the system is an open system, if the system is unitary evolving, then the output state would also be a pure state. And then we apply this operation S inverse. And whatever is the outcome here, we will do a measurement. So this setup, this kind of scheme is called time reverse metrology, because you do this operation S and then you do this operation S inverse. Now, as far as the quantum physical information is concerned, quantum physical information would be calculated using this part. So this part is not part of the quantum physical information. Quantum physical information is obtained from this output state, whether a pure state or a mixed state. So you can imagine that this part and this part together is part of the measurement scenario. A quick reminder about the squeezed states, two-mode squeezed state, which are generated by applying this operator on the vacuum. And we know many different ways in which we can implement this operator in the lab. So second order nonlinear interactions like parametric down conversion are exactly characterized by this kind of a Hamiltonian. You can do four-way mixing, and the four-way mixing is also characterized effectively by this Hamiltonian. So there are many different ways in which this can be realized in the lab. So the two-mode states are the pairwise quantum entangled states having this structure. So this implies that if there are n photons in one mode, then there are n photons in the other mode. In other words, probability of finding n photons in one mode is the same as the joint probability as it is illustrated schematically here. Now, each beam or each mode is thermal and therefore not useful. So what is the useful quantity here? It is the quantum correlation between these two modes. And so if you look at, for example, the intensity difference of the two modes, these would have very strong quantum correlated fluctuations, and this is what would be used in applications. Okay, so here is one example for the measurement, for the precise measurement of the phase, and where we use the two-mode squeezed states of light, and we will use a time reverse scenario. So this kind of setup is called the SU11 interferometer. And so here you have two modes which are in vacuum state. You apply this squeezing operation. One of the modes goes through an object which changes the phase of the incoming mode by this amount phi. The other mode goes unchanged, and then you do the reverse of this operation, S inverse. You have the output modes, and you look at the number of photons here, You look at the sum of the two photon numbers and the fluctuations in the sum. So this is the SU11 measurement of this phase. Now this setup is like the Mach-Zehnder interferometer. The only difference here is that we are not using any beam splitters. We are using here nonlinear elements or these squeezers and the anti-squeezer here. So as far as the experiments are concerned, what the experimentalist would measure, one is going to measure the mean number of total photons and the fluctuations in the mean number, in the number of the total photons. And so you define the error sensitivity, delta phi. So this is the fluctuation in the total number of photons at the output. And this quantity is the derivative of the mean number at the output with respect to this phase. And this turns out to be this. And the average number of photons at the output is 2 times sine hyperbolic square r. Therefore, this error sensitivity goes as 1 over the number of photons. And this limit is called the Heisenberg limited sensitivity. So that is the best you can do for the measurement of the phase. The standard quantum limit, if you use the, for example, coherent states of light, would give you a result which would be 1 over square root of n. So standard quantum limit has 1 over square root of n, and the Heisenberg limited sensitivity has 1 over n. Therefore, this measurement scenario enables you to reach the Heisenberg limited sensitivity. Let's now look at the same setup using the quantum Fisher information. So what we do, we use this input state and calculate the state at this point, and then calculate the quantum Fisher information. And the quantum Fisher information, this is a unitary system, so we can use this unitary result, and it gives you the same result. Therefore, this SU11 interferometry saturates Cramer Rao bound. So this is very interesting that we have the Cramer Rao bound for the measurement of this phase, and this kind of interferometric arrangement using the squeezed states of light can saturate the Cramer Rao bound. Now we can do something similar for the case of atomic interferometers. All we have to know is the corresponding analog of this. And we had actually worked on this problem many years ago in this paper. And what we have shown in that paper, how to generate analog of the squeezing operation. So this kind of a structure. So if you have a set of n atoms, n identical spins, and if you define this collective operator, you want to generate this unitary evolution. And what we have shown that if we use a cavity scenario, so we have atoms contained in a cavity interacting with a cavity field. And if you work in the dispersive limit, that is the frequency difference between the frequency of the cavity and the frequency of the atoms is large, then this can be transformed into a many-body interaction of this kind. So this is a many-body interaction, kind of a dipole-dipole interaction, which one is produced by the interaction of the atoms with the cavity. And so this can be transformed either to this form or to this form. And so effectively, we can generate this kind of a nonlinear interaction. Keep this in mind, this is Jx square. If you apply an external field, then the term here will always be Jx, linear in Jx. Whereas for squeezing purpose, we need Jx square. And so this is the atomic interferometric arrangement analogous to this. Again, time reverse setup. So you have this one which I described just now. Interferometric part, so determination of phase, the anti-squeezing operation, and then the readout. So again, if you look at this setup, if you start with all these spins in the ground state, this nonlinear operation produces a state at this point, which is this analog of the GHG state. So this is the n particle GHG state produced by this nonlinear interaction. And so GHG state is now used to probe this phase phi. And if you first look at this measurement, what you are going to do, you can, for example, look at the population in the excited state or in the ground state. So population in the ground state is going to be this, in the excited state is this. Note the factor n here. So this is a very significant factor that you get because of the usage of these states to probe the phase phi. And so then you can calculate the measured Fisher information in terms of these probabilities. And that gives you this value 1 over n. Quantum Fisher information you can calculate for this system. So you look at the state, quantum state at this point. From that you calculate the quantum Fisher information, and the quantum Fisher information is n square. So delta phi again is 1 over n. So you get the Heisenberg sensitivity limit for delta phi using these GHG states, which are essentially form of the squeezed state obtained by the application of this operator on the ground state. And again, this kind of a time reverse setup saturates the Cramer Rao bound. Okay, so now I want to describe to you an very nice experiment done by the people at NIST Boulder, and they looked at the time reverse metrology for the ionic displacement or the mechanical displacement. And so you have a ion in an ion trap. You prepare the center of mass motion in the ground state. Apply the squeezing operation. So remember that this is now doing the squeezed states of the matter, because we are dealing with the ion, center of mass motion of the ion. So this operation is squeezes the center of mass motion, and so this was the initial coherent state or the vacuum state. This gets converted into this squeezed state with the squeezing in x direction. You want to measure a small displacement of the ion. So this is the displacement operation. After this, you apply an anti-squeezing. So when you displace it, this squeezing ellipse gets displaced by a small amount. And then the anti-squeezing operation. And what happens in this case, remarkably, that the final one after this is again a coherent state, and the amplitude of this coherent state is magnified by the amount of squeezing, e to the power r. So e to the power r basically gives you depends on how much squeezing you are creating. So this is another example of a time reverse metrology, and this is very interesting. It's amplification of coherent amplitude with no addition of noise. So if you had not applied this S operation, just the displacement, it would be somewhere here. But this amplification is produced by the application of this S and S dagger, but no addition of noise. And mathematically you can prove it by just following these operations, that the output state, input state with vacuum will transform to this output state. And in this experimental paper, they showed that they can increase the measurement sensitivity by a factor 7.3. Okay, so this is the idea, and so how they implement the idea. So this is the ion that they have in a trap. And it has these two hyperfine ground state, this state and this state. And these are these, when you see 1, 2, 3, 1, 2, 3, these are the center of mass vibrational states, center of mass vibrational states associated with this electronic state, center of mass vibrational state associated with this electronic state. So those are the two electronic states. And yeah, Weinberg's group, they developed the pulse technology to perform transitions from one of the energy levels to one of the energy levels here. And this is done by the application of these so-called Raman beams. So you apply two laser beams and make sure that these laser beams are detuned from any of these excited states, so that no population is transferred into these excited states. Then the application of these Raman beams, it becomes like a James Cummings model of quantum optics and characterized by this Hamiltonian. So S plus and S minus will correspond to these two hyperfine ground states, and A corresponds to the center of mass motion. And so you can make a transition, let's say, from here to here. If you notice what you have done, you have gone from here to here, changed the electronic state, and changed the center of mass motion by 1 unit. So that's the James Cummings-like interaction. And for measurement purpose, they applied this, and then they applied an external field with phase phi. So the initial setup involves preparation of this state, do this to prepare the center of mass motion and keep the electronic state in this state. Then follow this up by the application of these two unitary evolutions. And then finally, you measure the population in this state, and the measurement of the population is done by the application of another field. So you apply another field, took it to the excited state, and look at the fluorescence from there. That's how you measure the population in this state. And this population measurement would depend on this parameter phi. And so you get an interference pattern here. And you look at the contrast or the visibility of the interference pattern. And by looking at this contrast, you define a signal to noise ratio. So signal to noise ratio turns out to be this. And C is given here. So you get approximately signal to noise ratio, and then you get it this factor G, which was related to the squeezing parameter. So this was the amplification of the initial displacement, and this was the factor e to the power r. And so by using these squeezing operations, you can enhance the signal to noise ratio factor by this e to the power r. And so that's the factor 7.3. Okay, so let's quickly analyze this setup from the perspective of the of the quantum Fisher information. So this is the scenario that we are doing. We are using this to prepare the initial probe. This is what we want to monitor, anti-squeezing and the readout. So quantum Fisher information is to be calculated by looking at the state at this point. And this quantum Fisher information turns out to be just this, which gives you the Cramer Rao bound for the displacement, which is this, and which just happens to be 1 over SNR. So this SNR, which is calculated here, happens to be this, provided this alpha I was small enough. So then we can compare the measured Fisher information. So the measured Fisher information will be obtained from these populations, maximum of the population, minimum of the population, taking the derivatives, etc. So this would be the measured Fisher information in the experiment, and this would be the quantum Fisher information. So here is a plot of the two as a function of the gain, which is e to the power r. For a small enough alpha I, the measured Fisher information coincides with the quantum Fisher information. That is the black curve. When alpha I increases, say this dashed curve or this one, then you start seeing deviations from this measurement then compared with the quantum Fisher information. So now you can ask the question, this kind of measurement optimum, and when you look at this, you clearly conclude that the measurement is not optimum if you increase the initial value of the displacement. For small displacement, it's optimum. Now it turns out that if you do a phonon counting, so which would be the analogous to the photon counting, so this would be the counting distribution for the phonons or the center of mass motion states. So then this measurement would saturate Cramer Rao bound. However, the phonon counting measurements are much more difficult than the measurement of the populations. So measurement of the populations basically would be the average value of these things. All right. So now the remaining time I'm going to spend on the open systems. So in open systems are the lossy systems, or the system can have a scattering loss. So I have a system here which is interacting. You use a probe beam, which is a coherent field, and you have an output signal. You have scattering and absorption losses. So S is the output signal, and we look at the noise in the output signal. Because this is a coherent field, so the noise is proportional to the square root of S. Therefore, signal to noise ratio is the square root of S. which is called the short noise limit or the standard quantum limit. So in order to do better than the short noise limit, you have to replace this coherent field by a quantum probe. Okay. So in order to understand what we should do, let's first look at this from the measurement perspective. So measurement perspective obviously involves the measurement of this mean intensity and the noise in the mean intensity. So we can do a simple calculation. We can do an input-output relationship. We can write output field in terms of the input field, and alpha is a measure of the absorption in this system. So this absorption in the system would be related to the damping and the length or the time that the light takes to travel the system. So the output fluctuations or the noise would be this mean value of the square of the photon number operator minus the square of the mean, and calculation shows that you can get for the sensitivity. So this would be the measured sensitivity in a typical experiment. You look at the fluctuations in the output and the derivative of the signal. And so this quantity, by doing an input-output analysis, can be related to the fluctuations in the input photon number, and the absorption. And now from this relation, it's clear that in order to minimize this delta alpha, you must choose an input that has the smallest fluctuations. And so if we set this quantity 0, then that is the best measurement that you can do. And that will give you delta alpha times 1 minus alpha for a single photon. And so this quantity, you want to make this to be 0. This would mean that I must probe this system with input Fock states of the radiation field. So I need the Fock states of the radiation field in order to get the best measurement for delta alpha. And we all know that it's very difficult to produce Fock states of the radiation field. Single photons we can produce, at least we have various ways in which we can get heralded single photons. There are other methods by which you can also get single photons. But if you want to think about few photons, it's impossible to imagine an experimental scenario which would give you a light beam in a Fock state with few photons. And so we'll have to find other methods which can give you as best value of delta alpha as possible. Now you can look at this from the quantum Fisher information perspective. And so for this problem, we need to calculate L of x. And this is an open system. So here you need to use the quantum master equation. And it turns out that you can solve the quantum master equation and find out this Lx, because for the input Fock state, you have a binomial distribution of the photons at the output. which enables you to calculate Lx at this quantity. And it turns out that the quantum Fisher information gives you a Cramer Rao bound delta alpha, and that's saturated by the focus state of the radiation field. In other words, if you use focus states of the radiation field, you saturate the Cramer Rao bound, and if you have this kind of experimental setup measuring the fluctuations and the mean, that will give you the same result as the Cramer Rao bound. So now the problem is that since we don't have the focus states of the radiation field, what else can we do? And that's what I'm going to tell you now, that how the single and two mode squeezed states of light can be we can use and see what is the best scenario. Okay. So for a single mode squeezed state, this is the kind of setup you can use. You have vacuum here. You have optical parametric amplifier. This produces a single mode squeezed vacuum. And then you have the absorber. And you can look at the output photon number. And you can calculate the quantum Fisher information for this setup and calculate the minimum value of delta alpha. And this turns out to have this expression. This is the value for the focus state written here. And so obviously, this value is not as good as what you have with the focus states. For a two-mode scenario, so we have two input vacuum states, optical parametric amplifier, and what you produce here at the output is the two-mode squeezed vacuum. And one of these beams go through the absorber, output here, and a measurement scheme. Okay. So I already told you what quantum Fisher information gives you for the single mode case. And let me tell you what this gives you for the two mode case. So for the two mode case, you can use the Gaussian state results because the Wigner function is Gaussian at this point, two-mode Gaussian Wigner function. And the two-mode Gaussian Wigner function, if such a field goes through an absorber, at the output, it's a mixed state, but it's still a two-mode Gaussian Wigner function. And using the properties of the Gaussian Wigner functions, you can calculate the output covariance matrix, and from that you can calculate the quantum Fisher information. And remarkably, it turned out that the quantum Fisher information using the two-mode squeezed states, so we calculate the state at this point and the quantum Fisher information, that this quantum Fisher information is same as the focus state. So which is quite remarkable, that the quantum Fisher information for a single mode case is worse than the focus state, whereas the quantum Fisher information for the two mode case is same as the focus state. So quite a remarkable result. And therefore, what this suggests, that we don't need the focus state as far as the measurement of the absorption is concerned. We can get away with the two-mode squeezed state, which we know how to generate in the lab. So here is a comparison of the Cramer Rao bound for the absorption measurement. for the one mode and for the two mode, and n is the sine hyperbolic square r, which is the number of photons going through the absorber. And it's not difficult to imagine the output of the OPO with this much photons. Not a problem. And so you see the two mode squeezed states beats what you get with the single mode squeezed light, and the two mode result is same. This blue line is same as for the Fock state. Okay, so this is the theoretical result using the Fisher information. Now the question is, what do we do in the experiment? So this is what I showed you. We calculated quantum Fisher information at this point using the field at this point. And what we can do, we can calculate the joint distribution of the photons at the output. And in terms of the joint distribution, we can calculate the measured Fisher information. In other words, if we can measure all of these, then we can calculate this Fi, which would be the measured Fisher information. And calculations show that this measured Fisher information is same as the quantum Fisher information. So a measurement based on these quantities would saturate the quantum Fisher information that we calculate using the two mode squeezed states of light. But there is a practical question here that if n and m are small, then we can imagine getting these p and m's. But if n and m could become larger and larger, it's impossible to imagine measuring all of these joint probabilities. So we have to have a more practical scheme for the measurement. And that's where our time reverse metrology turns out to be great use. Just give me a minute. I think I need to put my computer on charger. Okay, so this is from the measurement perspective. So this is the same SU11 interferometer. This is the absorber, open system here. Previously, we had phase element here. And the time reverse transformation is easily carried because you have a pump which is pumping this. We use the same pump to pump this, but we reverse the phase of the pump. So we change the phase of the pump by pi so that this OPA2 becomes inverse of this. So what we do in this measurement, we measure the total output photon number and the fluctuations in this photon number and use this to calculate delta alpha. And here are the results. So this is the delta alpha, if alpha is small, as a function of the photon number. There is a red curve here, and there is a blue curve here. Red curve is the result that you would get from this experimental setup. So that is the realistic experimental setup. And the blue curve is the prediction of QFI. And what we discovered is that these two almost match. And therefore, what we have shown that this measurement almost saturates Cramer Rao bound if alpha is small. Even alpha is 0.2, you start seeing some deviations. I'm sorry, I said it wrong. The dashed blue curve is the result of this experimental measurement, and the red one is the QFI. So this red is the QFI, and dashed blue is what you will get from this experimental measurement. So what this essentially shows that we can replace the Fock states by the two-mode squeezed states of light and use this kind of a time-reversed experimental measurement to get a result which almost saturates Cramer Rao bound. Okay, so this is another result. What's shown here, this is the standard quantum limit, and this is the two-mode time reversed setup, and there are dots here which are for the optimized single mode coherent squeezed state. So this extra element here is the coherent part of the single mode squeezed state, but you optimize. So that's what gives you these dots. So which again shows that the two-mode setup even beats this one. And this is, of course, the standard quantum noise limit. Okay, so I think probably I've almost used my time, right, Rupa?
Actually, a little over time. I also see people leaving maybe dinner time already. But
Yeah,
it is
so,
very, very
so I'm just
interesting.
going to conclude now.
Yes, please.
Okay, so, well, you know, we have shown applications of squeeze state of light and matter along with time reverse strategy to demonstrate definite advantage in quantum metrology for both open and quantum system. So this is basically the take-home message. And in case some people who want reference, they are listed here. Thanks very much for your attention.
Thank you very much. As usual, very dense, but you stated the problem and you provided a solution to so many different things, including really liked what came out of that Boulder, Colorado experiment on quantum amplification of mechanical oscillator displacement, the motion. Very, very nice. And I think there's several insights, including the last bit of how to actually produce an equivalence of the Fock states. So we'll note down the reference and probably allow us to get in touch with you with questions and comments. Because I think, Prashanta, we probably are running short of time. It's 8:07 already.
Yeah, but you can
really
still, yeah, entertain a couple of questions. Yeah.
Yes, I think it would be really nice if we could keep you for 2 more minutes and take a couple of questions from the audience. It's been really, really wonderful. Okay. Quickly unmute yourself and ask your question, whoever has a comment or a question. Yes, Harshvardhan.
Hello, Professor Agarwal. Fantastic to see you. Thank you very much.
Good to see you. Good to see you, Harsha.
Yeah. So I was just wondering, you did this for the absorbing sample, but if you have a scattering sample, there might be multiple paths. The experiment is going to be a lot more difficult because the paths might be very varied and all that. Does it make a lot of difference? Of course, this is
No,
an
but
open
you-
system, but yeah.
But no, you effectively look at the output and how much you have lost.
Okay.
That's all matters. That what is the
Okay.
net loss in the system.
I see. I see. So
Yeah.
it is, yeah, I see the point. Okay.
Yeah.
Thank you very much.
That's why this input output stuff works best, because you
Yeah,
just look at the output and how much you have lost.
Correct.
And
correct.
then I didn't show a quantum Langevin equation or the master equation, but that's what you need to use.
To calculate it. Yeah.
Yeah.
All right. Thank you.
Yeah.
Okay.
Ashok Kumar, please.
Yeah. Thank you, Professor Agarwal. It was very nice talk. So I was interested in SU11. Actually, basically what I learned in last few years, like people are trying to work on truncated SU11 interferometer, and they claim that they can get the sensitivity equivalent to full SU11. Just I was wondering, did you or can you comment on that, or do you look at those?
Yeah. So when people do the truncated ones,
Yeah.
they are doing homodyne measurements.
Yes, sir. Yes. Sir.
And my personal view is that we want to avoid the homodyne measurements as much as possible, because they are extremely difficult measurements to do and requires much more careful measurement.
Yeah.
And whereas the intensity measurements are much simpler, and
Sure.
and so their intensity measurements are definitely preferable measurements.
The problem, other way problem is also not very simple, because we have to undo, or we have to, whatever the first four-way mixer has done or nonlinear amplifier has done, we have to undo that, and then doing that also is quite challenging. Actually, it's not like
No, it is not, because one way you can do is sort of do a kind of reflection. So people, in fact, Maria Chakova's group in Erlangen, they don't use two OPA, they use only one OPA effectively.
I see.
And Maria Chakova has done lot of experiments.
Yes, I'm aware.
Yeah.
Yeah.
And of course, what you mentioned, this truncated one is Paul Lett.
Yes,
from
Paul Lett group.
Maryland. Yeah.
Yes, sir. Yes. So just one relevant question, actually. Since what your calculation shows that ultimately this SU11 is, basically inverting your squeezing operation, as S inverse gets cancelled, and finally it just appears to be displacement operator, actually. So aren't there any, another simple technique in which just applying a displacement operator, we can get this kind of advantages?
No, because the problem was that it has been known for ages that any time you want to amplify displacement, you add quantum noise. So all amplifiers add quantum noise, and once the whole purpose is to sort of minimize the noise here in order to get the best sensitivity. But on the other hand, if you have a procedure that adds quantum noise, you are not going to do in any way better.
I get it. Yes.
So what what remarkably this NIST group discovered, that doing this SNS inverse, that amplified the displacement. And in the atomic interferometer case, doing this S inverse to produce n times phi. So phi becomes n times phi. So you amplified a small phase by this factor n. And you did not add any noise. So let me just quickly go back to this to show you that you did not add a noise there. So I see on this slide, this was the initial GHG state. By going through the setup, it just became this cosine and sine, and the same GHG state.
Got it.
Yeah.
Yeah.
So,
thank you.
So you see now in all this scenario, you don't add any quantum noise. And I think this is a very big thing.
Yes. Great. Thank you. Thank you very much. Thank you very much. I liked it a lot. Thank you.
Very nice. I'm sure there will be many more questions, but in the interest of time, I think all good things have to come to an end. So I really thank you, Professor Agarwal. It's amazing. And from on our behalf, real good. Thank you to you. Thank you very much. Prashant,
Okay. Thanks everyone.
Yeah.
And very
Yeah,
nice
thank
seeing
you,
all
Prof.
of you.
Yeah.
Yeah. Bye-bye.
Bye-bye.
bye.
Thank you, Rupa. Thank you, Rupa, also.
Yeah, you're most welcome.
Yeah.
Bye.
Yes. Lovely.
Bye.
Beautiful. Thank you. Yeah.